Oh wow, I wish there were people to help me on this project. Wow!
So, in perfect physics world, mass is not supposed to affect the velocity of something going down a ramp because there's no friction. But we think that in real life, mass is going to affect it because friction exists in real life.
We will test this by building a ramp and sliding different weights down it, whilst timing it to determine the velocity of each block as it slides down the ramp. Then we will compare the results.
What you see now is our schematics diagram and our overall plan for the build.
First, we needed to measure the amount of wood needed for the ramp. As you can see, we did this by holding a tape measure from the base of the treehouse to the ground.
After we had all of it measured, we sketched out our basic design and moved to cut the big piece of plywood into segments for the ramp.
Next, we needed our pieces to slide down the ramp. We had to make friction a constant so that there was going to be no difference between each of the four weights. So we had to use the same wood plank for this job. We cut a wooden plank into 4 segments to slide down the ramp.
See, afterwards he realized that he didn't need to cut each piece because we had a circular saw, so we quickly just cut it like that.
Next, we needed a brace to connect the previously cut plywood together, so we cut 3 wooden planks in order to secure the 2 plywood segments.
Here we are securing the 2 plywood segments together using the 3 wooden planks and deck screws in order to make sure the fulcrum of the ramp doesn't cave in on itself.
To simplify what we were saying earlier is, the hypotenuse was not connected here. We had 2 different sheets of plywood, so what we did was we added an underboard sheet and connected it with screws like this.
True engineering right here. Zip ties and a lot of ingenuity.
We came up with the idea of using zip ties in order to hold the weights down to the wooden planks, so we drilled holes into the wooden segments to be able to secure weights to the wooden plank.
In order for the zip ties not to change the friction of the wood, we created channels in the wood to hold the zip ties and ensure they stayed within the wood block and didn't touch the plywood ramp when sliding down.
Can we get a shot of that?
Big man working hard.
Alright, so you want to...
Here we're making sure that the mass of each weight are the same as the value given on them, plus adding the mass of the wood secured to the weight. We found there are differences in the actual weight of the object versus what was presented on it.
Alright, Luis. It's funny you think about that.
Pizza trip.
Pizza acquired.
The pizza has been acquired.
Pizza time.
After we finished eating the pizza, we realized we still had a lot of work to do, so we all had to work together and pool our efforts to be able to finish on time before everyone had to leave. Here we were just measuring the ramp once more before we head outside.
What's in between 169 and 170?
169 and a half.
I'm putting 14 feet on the sheet.
Here we are carrying out all the supplies.
Lift it up now. Left, right, right, left. Left, right, right. Oh no.
Here you see us hoisting up the ramp, as well as putting 2 support brackets under it. Carson is now screwing the top part of the ramp into the treehouse.
Let's get an action shot of this.
Ooh! Look at that beast of a man.
Here we're making the end piece so we know when to stop the timer.
Watching this back, I'd like to point out this death trap right here. Using our knowledge from PoE, we know that the triangle is the strongest shape in engineering. Thus, we decided to build support trusses under our ramp to ensure that it stays secure.
I mean, it holds using that engineering experience.
6 foot, 7 foot.
The way this experiment works is I will call out a time from the top of the ramp and drop the weight. Then Luis will start the timer. Luis will stop the timer once it hits the base plate which Carson's at. We repeated the experiment 3 times with each weight.
Test 3, 10. 3, 2, 1, go. 3, 2, 1, go. 3, 2, 1, go.
After we collected all our data, we decided to do a test and see how much stress our ramp could hold.
You're not gonna live through this.
Tell me, who was Earth's best defender? Assassin's Creed, just the one. We worked all day for this. Can you say that again? Hey, what was that?
Miss Mara only taught me how to use an Excel sheet. And she didn't put me in Arrow.
He didn't make it into Arrow.
He didn't make it in Arrow.
Since Carson's so good at Excel, he made a spreadsheet. On this spreadsheet, you see all 4 weights, accompanied by all 3 of their times, with the average time across the 3 times. You also see final velocity and acceleration.
After we found the times for each respective weight sliding down the ramp, all we had to use were kinematic equations number 1 and 2 to find the velocity. We used kinematics equation number 2 to find the acceleration by substituting as shown in the picture, and we solved for velocity by plugging in the acceleration and the time for each respective mass, finding the final velocity. The distance that we used was the horizontal distance of the triangle, 12.1. Our findings show that an increase in mass leads to a decrease in both acceleration and velocity, proving that our hypothesis was correct. This happens because an increase in the mass leads to an increase in force normal, which is directly tied to an increase in force friction, which acts against the block as it goes down the ramp, slowing it down, decreasing both its acceleration and velocity.
We're in a neighborhood, by the way. I can't believe we haven't got a noise complaint.
I'm really surprised we haven't gotten one from right here.
Yeah.
Considering we've been hammering and
Look at how close we are to this house. And we haven't got a noise complaint. That's a window. That's a window right there. I am actually very surprised.
there's a good chance there's people right there.